Dosimetry note. It is a generally accepted laser principle that the more chronic an area, the greater the energy required to cause a therapeutic effect. Conversely, the more acute the problem, the less energy used to irradiate the region. The amount of treatment time per point will vary depending on the average power rating of the lasing device being used. This is where a more powerful laser has the advantage of being able to saturate an area with light energy at a faster rate, leading to considerably shorter treatment duration times. This has implications for clinical efficiencies when treating multiple patients throughout the day. As an applied example, if a clinician intends to irradiate an area with the target dose of 1 joule and we compare three different laser power output levels, we find the following. A 1 milliwatt laser beam would require 1000 seconds to achieve this dosage, whereas a 10 milliwatt laser would require 100 seconds and a 50 milliwatt laser approximately 20 seconds to make dosage. If the target dose is closer to 10 joules of energy, we can see that these irradiation times are multiplied by a factor of 10. If we are treating multiple trigger points, 5 to 6, we can now further multiply the total time by 5 or 6 times. It is this scenario that has laser manufacturers scrambling to develop more powerful laser systems. Laser frequencies are often a point of discussion and debate as they relate to cold laser application. There are many manuals in existence written for the most part anecdotally, whereby authors passionately make an argument for the importance of frequency modulation, chopping a continuous wave into various frequency cycles or pulse bursts, sometimes altering the pulse amplitude width and interpulse interval. Whether there is strong evidence at this time that a pulse frequency affects a specific clinical condition is not clear. That is not to say that future research will not elucidate key frequencies as optimal for therapeutic goals. There is in existence an entire library of information that supports the physics of frequencies in general, sound, light, electrical, etc., as being important in achieving certain characteristics such as conveying intelligence in radio waves. Authors such as Paul, Nogier, and Barr all wrote about resonance theory and how frequencies transfer kinetic energy to electrically charged cell particles and also can transmit specific information. We know, for instance, that electromagnetic frequencies in brain research are associated with certain bodily reactions such as delta waves for deep sleep and gamma waves in stress. In any case, the role of laser frequencies remains an open area for clinical investigation. Tendinopathy. There have been numerous reports published that support the beneficial effects aspects of low-level laser therapy in tendon healing through lasers, positive effects on collagen tissue. Envemeka et al. Reported that several laser types including helium neon, gallium arsenic, and gallium aluminium arsenic are all promoted beneficial effects on tendon healing when combined with ultrasound and early weight bearing over those of ultrasound and early weight bearing together or in isolation with laser. The authors noted improvements in biomechanical and morphological indices of tendon healing. A clinical study using 176 patients with tendinitis conducted by Lodberg, Anderson et al. Found that laser application significantly reduced the morbidity associated with acute tendinitis over a 6-session treatment course. Similar findings were corroborated by Jordal et al. In 2001. Thomason and Proanka et al. Energy densities ranging between 5 and 20 joule per centimeter squared and wavelengths above 800 nanometer are recommended for deeper penetration capabilities. No more specific dosage recommendations can be provided at this time since more research is required to elucidate more precise dosages. Practitioners who treat facial points for conditions such as neuralgias or TMJ syndrome will irradiate at dosages approximating 1 to 5 joule per centimeter squared and may experience success with either helium neon or deeper penetration lasers such as gallium aluminum arsenic. Laser practitioners also apply this mode of treatment to various forms of tendinopathy, including medial and lateral epicondylitis, plantar fasciitis, rotator cuff, and various other endopathies. All these conditions have been studied using laser as a primary form of treatment with varying degrees of success. There is such a wide variation in treatment response noted in these studies, which is consistent with the wide array of dosages parameters used, not to mention wavelength choice, which is crucial for proper penetration depth. The majority of no difference trials have used a helium neon laser source, which has the least penetration power of any laser coupled with low power density capability. The end result is negligible energy density and not a high probability of a therapeutic effect. Unfortunately, many clinical trials have been accidentally undermined from the start with the poor dosage selection parameters. Investigations utilizing higher energy densities, more than 3 joule per centimeter squared, were more likely to show a statistically significant difference between treatment and control groups. Wound healing. There is considerably more and better research support for the use of cold laser application in wound healing perhaps than any other medical condition discussed so far. In 2004, Woodruff et al. Published a meta-analysis on the subject and concluded that laser therapy is an effective tool for promoting wound repair. This conclusion draws support from many others who have investigated the use of laser in wound healing. One of the primary laser-mediated physiological benefits to a wound is that a laser will increase the amount of collagen formation in the irradiated region. Laser has demonstrated to have positive effects on both macrophage and fibroblast cell lines. A more recent finding has been that certain laser wavelengths such as the 630 nanometer helium neon has an inhibitory effect on certain bacterial strains including E. coli. This has valuable implications for the treatment of infected wounds. There have been quite a number of significant in vitro and in vivo findings as they pertain to cold laser usage that would help explain many of the empirical or observational reports that are pervasive in the literature today. Nicola et al. Found that laser biostimulation of rat femurs over the course of 8 days using a 660 nanometer wavelength and dosing the lasing site at 10 joule per centimeter squared had a positive effect on bone cell activity, both resorption and formation around the site of repair without changing bone structure. Similar findings were reported by other researchers who also reported increased trabecular bone growth along with a hastened collagen matrix organization. Other cell lines, including monogenic types, including the muscle satellite cells, have also been shown to affect by LLT. Specifically, lasers' ability to increase the number of satellite cells around isolated single muscle fibers. These findings are bolstered by NASA studies on light-emitting diodes, as reported by Velan et al., concluding that light therapy has been found to increase fibroblasts, osteoblasts, skeletal muscle cells, and human epithelial cells. Their work was performed primarily on rodents, but the authors feel that it is only a matter of time before similar findings are corroborated in human studies. A special note regarding the role of NASA in laser research would be appropriate given the scope and magnitude of this agency's contribution the role of light therapy thus far. Studies on cells exposed to varying levels of gravity have concluded that human cells require gravity to stimulate growth. This requirement poses significant challenge to those astronauts involved in long-term space flight. NASA developed LEDs as a way in which to simulate the basic but essential mitochondrial process of each cell so as to provide not only tissue healing but also to minimize bone and muscle atrophy. NASA views LED technology as a promising alternative to medication and surgery whereby the biostimulation of natural regenerative mechanism would be the primary goal. In regards to wound healing, the NASA project has demonstrated that wavelengths between 670 and 880 nanometer at total energy levels of 4 to 8 joule per centimeter squared applied at power densities of 50 milliwatt per centimeter square are optimal parameters. Conclusion: there continues to be a pressing need for properly controlled, randomized clinical trials in the field of laser therapy. It is not difficult to see that these devices could impart powerful placebo effect in even the most skeptical patient. The research base regarding lasers is only as good as the methods and designs implemented in the individual trials comprising the base. There is more reason to be optimistic than not, however, since more product interest will necessitate an increased push for better research validation. Those practitioners who have used cold lasers on a regular basis will in many cases remark that absence of evidence is not evidence of absence. I would have to agree in the case of cold laser. For the most part, many of the authors who published manuscripts that found no difference between control and treatment groups have stated in their conclusion that more research is recommended and furthermore, more research is warranted. The in vitro and in vivo studies clearly have demonstrated that dose and wavelength are critical in achieving therapeutic goals. Yet, many reports fail to fully describe both parameters. This is not a failure of modality under study, it is a flaw in the study design. Core lasers are slowly working their way to becoming commonly used therapeutic modalities of choice in the treatment of painful conditions of musculoskeletal origin. More work needs to be done in elucidating human dose response relationships and condition specific optimal wavelength selection. Ultimately, it will be the day to day performance of cold lasers on patient problems that will have the most impact in deciding the clinical place cold lasers will occupy in the therapeutic milieu, quite apart from the research support. From this perspective, the introduction of cold laser in the field of pain management could supersede the growth pattern of many of our more contemporary modalities.